All right. So welcome everybody out to the Python Users Group meeting. This week we are going to talk about the itertools library. And I would like to throw a question out there for the general audience. Is anybody not familiar with the concept of iterators, whether it be in Python or in general? Because if you don't understand what an iterator is, it will be easy to get lost during this presentation. So if we need to spend a few minutes going over iterators, we can do that first. Does anybody need a refresher on what iterators are and how they work? Okay. Well, let's see. It may, so Shant asks, I don't, but it may be a technical term thing. Okay. Well, I've got two code examples here. It is not just a loop. So the distinction, so let's talk about it for a few minutes. So there's an important distinction here because an iterator itself has nothing to do with looping. An iterator is basically just an object with a special interface for asking for objects repeatedly. And so it's important to distinguish it from what people normally think of when they think of like looping over a list and what an iterator actually is. So I've got two examples here in C. The first one is a traditional for loop. So this just prints out hello world 10 times. And really what this for loop is it's syntactic sugar for this code right here, where we just have a loop where but before we start the loop, we initialize a value, and then we check for a condition. If that condition is false, we break out of the loop, and then we have some value change at the end. So this while loop is the equivalent to this for loop. So this for loop is just syntactic sugar for this while loop here. Now this is just all this is it's conditional looping. That is not the same thing as iteration. In C, there is not a concept of iteration built into the language, or I believe in the standard library. In C++, there is iteration supported in the standard library, and it's basically a specific interface provided by certain object types. Now, the question then becomes, well, if I have this way of looping over, say, like a list, now in this case, I'm just printing out hello world, but if I could use this I variable as an index into an array, and then I could act on an array, each step of the array. Well, what if I had a data type that wasn't indexable? Like there wasn't a fixed order to the values inside. There wasn't a way that I could say, give me the third object, or give me the third value in this container. Well, that's actually a real problem, and it's one that you would run into a lot in Python because Python leans very heavily on unordered data types, specifically dictionaries, or if you're coming from a C++ background, it would be like a hash map or something like that. It's effectively the same type of object. So in Python, they rely very heavily on the concept of an iterator. So what's an iterator? An iterator is an object where instead of asking for the value via an index, you get an iterator for that container, and then you ask it for the values one at a time. So let me pull up my console here, and I will show you an example. So we're going to create a list, and it's going to have 5 values in it. And in Python, I can do something like this. So for I in range, and we'll say range 5 because that's the size of our list. And then we'll print oh, thanks, honey. My wife just brought me lunch. She is wonderful. And then for each step in the values from 0 to 4, I can ask for the ith value of my list A. Now the range function that I'm calling here is basically creates an iterator that behaves exactly like this for loop here. So if I changed it to a 5, it would be exactly equivalent. And so what it does is for each step through my loop, it's giving me 0, then 1, then 2, then 3, then 4, and then it breaks out. So if I run this, I just get all of the values in my list. And that's, it's useful, but it's not great. So normally what you would do, the way you would normally do a loop like this is for v in A itself. And then you would, there we go, print. And then you would print v. And that will give you the values one at a time in the list. So what's going on here that's different? So A actually provides an iterator interface. So we can actually ask for that that iterator interface ourselves. And so an iterator is an object. And so if we want to get the iterator for A, we can do iter A. And now let's see, type of I is a class, it's a list iterator. And so now what does that mean? So I has a couple methods on it, but the important one is next. Is it next or is it underscore next? I can't remember if they changed it to 3. Let's just try it. Okay, that's right. It's double underscore next. This is different from Python 2, and I always forget. Okay, so every time we call next, it'll give us the iterator object will give us the next thing in what it's an iterator for. And then in Python, when we call next and there's nothing left to retrieve from our iterator, it raises a stop iteration exception. And so that's the interface for iterators in Python. Now, of course, this begs the question, why would you bother to do this or make this interface available when you could just ask for, do essentially the C equivalent and just use indices to ask for the items in the list? Well, what if you have what if you have something that you can't index directly? So for instance, if we have a set, so if we have a set, the set is not directly indexable. Set object does not support indexing. However, let's see, we can get an iterator for S. And that will give us the items in S. Now, this just happens to give them back in the same order we put them in. But because sets are unordered, we don't know the order they're going to come out, so we can't assume anything about the order. In Python dictionaries, we can get the values out of a dictionary as of Python 3.6, those values come out of the dictionary in the same order you put them in. It wasn't just an implementation detail in 3.6. In 3.7, they codified that behavior. So, yeah, but you normally wouldn't assume anything about the order that values come out of a dictionary. or a set. So that's a high-level view of what an iterator is. It's basically an object with a next interface that you can call. When you write a for loop, so when you do a for loop, this is syntactic sugar for ask A for an iterator over it, and then step over it and assign the value returned by next to V, and do that over and over again until you get a stop iteration exception and then break out of the loop. That's what's happening there. So usually you're using the for syntax to step over the values of an iterator, but it's not actually required. So when you'll see in documentation in Python, you'll say this function accepts any iterable object. That's what it's doing, is it's expecting to be able to get an iterator for that object and use it to generate the values from it, and then do whatever the function is supposed to do. The other thing about iterators is there doesn't actually have to be an underlying data container. So you can actually create an object that has this interface that just returns values forever. Or like back when I was learning Python, I had an assignment in school that says create an iterator that produces all of the prime numbers. Now, after a while, it slows down. It starts running pretty slow, but you can do that. So it's just a matter of creating an object with the appropriate interface that will produce values. So having infinite iterators is totally a thing that you can do. It just, instead of like going to an underlying data structure to grab values, it's calculating them. So that's a reasonable thing to do. And in fact, some of the iterators that we're going to talk about generated from itertools are infinite. So does that clear up any confusion about what an iterator is and what it's for? Feel free to answer in the chat or out loud. I'm going to take a bite of my lunch. Okay. Oh, hold on. I have a phone call. Hello? And it's spam. Great. I will edit that out of the video. Okay, so I'm glad that helps. We have a question from Shant. How are iterators different from generators? They are. They actually have a lot in common. A generator is a function that when you call it, it creates an iterator. So what Shant is referring to is a generator is basically a function with a yield statement in it. So if we do def ITR, now let's not call it ITR, let's call it IT, and let's see, we won't give it any arguments because we're going to keep this as simple as possible. And I'm making stuff up here as I go. Okay, yield yield I. Okay, so this is a really simple example of a generator. It's just a function with a loop in it, except instead of calling return, we call yield, and then we can create an instance of our iterator equals IT, or we can create an instance of our generator. Well, if we look at the type, we say that this is a class generator, but it has the same interface as an iterator and can be used anywhere that you could use an iterator. So we can do I._next. And what it will do is it will execute until it reaches the first yield statement, and then it stops. And it returns that, and next will return that value. We can call it again and get the next values. So really, a generator is a function that returns an iterator. And so this is all handled, the state is managed, of the function is managed internally by Python. This is really, really handy if you want to create a way of creating iterators, because otherwise you would have to create a class. The class keeps track of your state. This gives you a very convenient way of describing an iterator in terms of a function. And you can have as many yield statements as you want. It'll just, when you call next, it will resume execution until it finds the next yield statement. It will stop there. Return the next will return that value. And so you can have 15 yield statements. You can have one. You can have a function that just doesn't have a looping structure like this and just has like 3 yield statements. And then when you call it, you'll get an iterator. You can call next 3 times and get the 3 different values out of it. That is actually something that we've done in Voltron in the core agent class. It uses that paradigm. So yeah, a function generator is a function that returns an iterator, and calling next on it will yield whatever is in the statement. So that's the difference between an iterator and a generator. A generator is just a really convenient way of creating an iterator. Does that help you, Shant? Okay, good. He replies, great, thanks. Okay, so now that we have a good grasp of generators and iterators, we're going to go over the itertools library. And a lot of these I'm just going to, I'm not actually going to write code examples, or I might, but for the most part, I can demonstrate a lot of these in just in the command line here. So we're going to do import itertools as I'm going to shorten it to IT, so I'm not typing a whole bunch here. So itertools is basically tools for either creating, mostly it's for creating iterators of special types. And so there's all sorts of like looping constructs that it can do for you that will help you simplify your code. And there are some caveats to using itertools that I will kind of cover in general terms at the end. But it's mostly has to do with when not to use itertools, because once you realize that it's there, you want to use it all the time, and it's not always appropriate. Okay, so let's start with some of the simple infinite iterators. So there is a cycle, a count, and a repeat iterator. Oh, and if you want to follow along, let's see. If you want to follow along in the documentation, I will post that in the chat. Here's the itertools documentation page. I'm not going to cover every single function in here. I'm going to mostly cover the ones that I've used in practice, because those are probably the ones that you will end up using as well. So let's start with, and in fact, since I'm just going to be working off of examples here, why don't I go ahead and bring the documentation window over here so we can all follow along together. All right. And hopefully everybody is able to read that. Okay, so to start, there's a couple of basic infinite iterators that we can use. So we have count, cycle, and repeat. And I'm not going to stick, and as we're using these, I'm just going to, instead of putting them in a for loop, I'm going to just call the next method a few times so you can see what it's doing. And that will simplify things for us. So if we create an iterator called count, let's give it a starting value. Oh, count is not defined. Helps if I do IT. There we go. So now I is now an instance of itertools count. If we call next, it will start counting from whatever value we give it, and it will count forever. So it's basically just an infinite loop counting up from wherever you tell it to start. We can also give it a step. Let's say 5. And this will, and of course, because we've recreated the iterator, it starts over from 10, and then it counts by 5s up forever. We then have the cycle iterator, which takes as an argument another iterable. So the example that they use here is a string. Strings can be iterated over like anything else. If you ask for an iterator for a string, it'll give you the characters out of that string one at a time. And in this case, cycle goes through the iterator until it finishes and then just starts it over. So it's an infinite loop cycling over an iterator forever. We have the repeat iterator, which will repeat a value either the number of times that you tell it to, or will repeat infinitely. There's no sense in demonstrating that. Okay, some of these iterators are actually new since the last time I've looked at this documentation. So I will cover one or two that I've never used before just because I think they're interesting. So the next one is accumulate. Accumulate takes, this is not an infinite iterable, but it is, it takes another iterable and gives you the running total. So if we do, let's see, where's their example here? Yeah, let's use data. Control V. So if we have data and then we do accumulate, so let's see, I equals IT dot accumulate data, accumulate. Typing is hard. Okay. And then if we call next, so what this does is this will give you the running accumulation as it steps over the list. And it uses the accumulation by default is addition. So if we call next, we say, okay, well, we have 0 plus 3. That's our first value. Then 7, then plus 6, then plus 2. And it will go on and on and on as long as there's still data. So that's what accumulator does. And then we can specify an accumulate function. So let's do import operator. And then we can specify like operator multiplication. So this is the multiplication operation as a function. There we go. And so it starts out with 3, 12, 72 times 2 is going to be 144, times 1 is going to be 144, times 9 is going to be 1296. So that's the accumulate operator. Very, very handy for running totals as you're stepping through some other iterable. Okay. So the next one is chain. Chain is handy because it basically allows you to chain multiple operators together. are multiple iterators together. So if you wanted to do this by hand, you would say, so let's define data 2 as something like that. Now let's say that we wanted to run the same loop. We wanted to run the same loop multiple times, but we wanted to run it over one set of data and then another set of data. And so to do that by hand, you would have to do something like this: for I in, or let's see, for D in data. Let's see, let's put it in a tuple: data comma data 2, and then let's see, for value in D, print D. This is Python 3, so that's a dot function. Okay. Oh, I did that wrong, but let's see. Print V. There we go. So that's how you would do that, is you would have to do it with a nested loop. If you wanted to simplify that, you could do it chain, let's see, and then chain takes a, it can either, let's see, yeah, you for each you give it a list of arguments, and it will chain them together. So we could do data comma data 2, and then I underscore, something like that. And then you could go through, and then when it gets to the end of the first one, you can go to the second one. Now, if you don't know how many arguments you're going to have in chain, there's two things you could do. You could either put all of your arguments to chain in a list and then do the star args method of calling the function, or you can call chain from iterable, which instead of having a list of arguments that are the things that you want to put together, you could do this. So dot chain from iterable, and then you could give it a list of values, and that's equivalent. And that way you can build up a list of as many things, or either you can either pass it in an iterable. So you could not use the star args if you want to use an iterable as your argument to if you wanted to use something other than a list to tell it how many iterables that you want to chain together. So this allows you to do that. So instead of a list, I could pass it in like a generator or something like that. You can't use a generator to populate a star args argument, but this would allow you to do that. So I could have a generator that's spitting out more iterables, and then this would just chain them together. So, okay, let's see. So let's look at another good example. Okay, so in Python 3, they changed the way the zip built-in worked. So the zip built-in in Python 2 returned a list, and that was limiting because you wanted to, usually you just wanted to step over it, so you didn't need to actually create the list object. So in Python 3, they changed the zip to where you gave it a set of iterables, and it would it would return an iterable, which you would then step over. Then if you wanted to turn it into the list, you'd have to do it by hand. And in Python 2, if you wanted that same behavior, there was a function that you called an itertools. Well, now that's how, because that's how it behaves by default in Python 3, that equivalent function in itertools went away because it was unneeded. So to explain what I'm talking about, let's do I equals zip. So what zip does is it takes any number of iterables and it will step over them in lockstep and return a tuple of all of the values. So if we do zip, let's see, ABC, D, and then if we do, let's see, 1, 2, 3, something like that, we can call next, and that returns a tuple of the first item from the first iterator and the first item from the second iterator. And we can just do that until one of the iterators is exhausted. That's when we get our stop iteration. So you'll notice that our first argument would return more values than the second one. So it will stop as soon as one of the iterators runs out. This is really handy if you want to take multiple lists and stitch them together and step over them in lockstep, which is a surprisingly common thing to do. So, but what if we wanted to ensure that we consumed all of the items in the list? Well, itertools has zip longest. Zip underscore longest. And what this does is instead of stopping when one of the iterables runs out, it starts dropping in a none when there are no more values available. And then it will fail. You can also specify the fill value for the empty iterable if you would like. So this one's handy as well. Now let's talk about the combinatoric iterators, and these are helpful for removing nested for loops from your code. So the one that you see the most commonly used is called product. So let's call that guy. In fact, let's use the same arguments that we have here. Product. Let's see if I did that correctly. Okay. So what this does is this is like you would compare it to an odometer in the way that it steps over the different iterators. So it takes the first value from all of the iterators, then it takes the first value, it keeps the first value from the first iterator, and then steps up this to the second value of the second iterator, and repeats until the last iterator runs out, and then it goes to the second value of the first iterator and back to the first value of the first iterator. So it's like an odometer. And you can put as many iterators in here as you want. I'm getting a wild hair here. I'm sure I spelled those wrong, but I don't care. And so it'll count up like that. And this is the equivalent of for I in ABC and then nested in that for J in 1, 2, 3, for K in do re mi, and then doing something inside of that inner loop. So it allows you to take those nested for loops and squash them all down into a single line of code. Now, let's see. We also have, and some of these I have to run because I forget exactly how they work. So we have product, so that's how product works. Then we also have permutations. It takes at most 2 arguments, 3 given. Okay. All possible orders. No, okay. I got to look at the example here because I forget how this one works. Oh, that's right. That's right. Okay. So permutations gives us all of the possible permutations of all of the values in an iterable. So if we do something like this, this will take all of the values in our iterator. Come on, there we go. And it will step through all of the ways that they can be ordered. And I believe since there are 3 items, this should be 6. Yeah, and that's the last one. And so this will give you all of the permutations of what's in your what comes out of your iterable. Let's see. Okay, combinations is the same thing. Or combinations is, well, no, that's not correct. Combinations gives you all of the combinations of combinations combinations is best described as, oh, that's right. I'm doing that wrong. 2. It gives you all of the different combinations of elements in your iterator. So there's only going to be 3 in this case: AB, AC, BC, and then that's it. So without any repeats. So as opposed to permutations, which is basically the nested for loop, this is all the different subset. Here's the correct way to describe it. It's all the different subsets, all the different possible subsets of length 2 from the input iterator. And I've used this one quite a bit in some in a project for calculating. Oh gosh, I forget what it's called now. I don't want to say anything because I know if I say it wrong, if I say it out loud, I'll say it wrong. Yeah. So that's the different combinatoric iterators. Let's see. Trying to think if there's anything particularly useful from the terminating iterators that I missed. I can't think of any. Does anybody have any questions?
Hey Kyle, this is Sean.
Yeah.
That'd be easier to talk than type.
Yes.
Question. So how do iterators compare with respect to for loops in terms of speed?
In the context of Python?
Yes. I would imagine that there. So I also program in R a lot.
Uh-huh.
Due to slowdowns of slowdowns in using for loops, it's encouraged to use things like I'll apply, which
Right.
is the function to all the elements in a list or an array.
Okay.
I'm
So
wondering if the iterator has some kind of
penalty.
effect. Well, penalty. I mean, is it really a penalty, or
It,
because I know Python suffers from the for loop slowdown as well, and I'm just wondering if
yeah, and that's
they
correct. Well, so in Python, what you're generally going to deal with. So let's discuss this piece of code right here. This is always in C. This is going to, or and let's say C++, because C++ actually has iterators. This, if it's possible to do, is always going to be faster than using an iterator, because so I don't have like an object here that I can reference. So let's say int a, oh gosh, and I'm going to get this wrong because I don't ever write C code anymore. Let's see. 1, 2, 3, 4, 5. Okay. And like I say, this is not going to be correct. Let's see. Equals a something like that. Okay. So this operation right here runs in constant time, because a in C, a is an address, and so this is based when this right here does a calculation as an offset from that address, and so it's about as fast as you can go looking up data in on a modern computer. It's like I say, it's constant time. It does it's one simple multiplication and an addition operation to find the spot in memory to resolve this. So that's always going to be super fast. Now in C++, when you have an iterator, you have the overhead of, you have function call overhead, because you're calling a function on the iterator object. You the resolution of finding the value for the iteration is, it's not always going to be constant time. In the case of like say you've got a binary search tree and you've got an iterator over that binary search tree, it's going to be close but not quite constant time, because when you say next, it might just be able to take one step down the tree, but sometimes it has to like recursively climb back up the tree in order to find the next value to return. So sometimes what it is just the thing that you're stepping over. There's some extra work required to calculate the value, which is one of the advantages of iterators over this, is you've got all this flexibility as to what you can do. Now in Python, the real question is where is your code executing in terms of performance? So when you write a for loop, that's going to be all Python code. But is that for loop something that can be executed like down in a C library instead? And that's actually one of the interesting things about the itertools library, is like the combinations function. Let me pull that back up here. Like product. Somebody here at work, here at my work, used product to replace a bunch of nested for loops. What that did is that took the actual for loop part of the code and moved it off into C, into having that be executed in C code, because that's something I forgot to mention, is all these iterator functions are written in C, designed to work with Python objects, but the actual nuts and bolts are implemented in C, and so they are dramatically faster than the equivalent Python code. So yeah. Now, as far as like would I be better off writing the equivalent, is, which is better in this case? 1, 2, 3, 4. Am I in Python, am I better off doing this? Or am I better off doing what I showed before, for v in a print v? Which one of those is going to be better? And this one's going to be faster because we're actually introducing extra steps in this code. And ultimately, if I were to try and do the equivalent to the C, the C for loop, I can't, because I have to use this range function in order to get the same functionality. And so if I did this, which is the equivalent, which is I can do this in Python, it's going to be slower because I'm doing in Python things that could be happening down in the interpreter, have the interpreter handle that for us, down and have it do it in C code rather than trying to basically emulate it in Python code. Does that answer your question? That was long-winded.
It kind of does.
So
I'm still not sure if the iterator is actually.
In Python, you want to use iterators where you can.
Okay.
And it really, and when you're thinking of things in terms of like performance, if you can get things out of Python and into a library that's doing the same thing in C code, like using the iterator libraries, and this is if you're concerned about performance, then that's the way to go. If you're doing doing things with like matrices and stuff like that, you don't want to do that in Python lists. You want to use NumPy arrays because those are just, and then you're not going to use for loops to step over the items in the NumPy array. You're going to use NumPy functions to do the equivalent of what you would have done with a for loop. That's going to be much faster.
Okay, great. That does answer my question. Thank you.
Yeah. And and again, it depends on what you're doing, because if you're doing something where optimization is important, then you start looking into the libraries that you can use to make it go faster. I mean, the other thing you can do is you can look into Python, which converts Python code into the equivalent C code, because everything that you can do in the Python interpreter or through the Python programming language, you can also do in C using the Python C API. And so Python can take just regular Python code and convert it into the equivalent C code that uses that API. And that'll give you a speed boost right there. But then the other thing it can do that's really handy is it can convert, you can start adding type annotations into your Python code. It's no longer Python code at that point, but you're basically giving Python the information it needs to remove the need to use actual Python objects for doing work, and that can be a tremendous performance increase. And one of the things that Python does, one of the things that it can do that's really smart, is it can take something like this code right here, this for I in range 10, and convert it directly into the equivalent for loop once you've given it enough information that says, oh yeah, I what I need to do is actually this, and then it's like 1,000 times faster. So that's something that you can look into if this stuff is performance, if what you're working on is very performance critical, because we've seen performance boosts of like 300 to 400 times faster in real practical applications. The toy examples on the Python page are not really indicative of the performance increases you can get, because they show performance increases of like 1,000 times faster. in practice, you're usually not going to get that much of a performance boost, but we've seen realistically, 300 to 400 times faster code. So that's something worth looking at. But that's kind of a rabbit hole, because the learning Python takes quite a bit of effort. I have covered it in the past, but while I was still at PNNL, so that video of actually I didn't cover it. Shwetha covered it. Let me be clear. That was done behind. That video is behind the firewall at PNNL, so I don't have access to it anymore. Does that help?
Yeah, thank you.
Okay, good. Are there any other questions? Okay. If not, we will call it a meeting. Thank you for showing up. And one thing I did mention in my email that I was going to talk about, things that we were upcoming plans for the meeting. Because there were a lot of good videos that are now stuck at PNNL or are never going to see a public release. I'm probably going to recover some of those topics again. And unless you were there for that original set, which I see lots of new names on here, unless you were there for that original set of videos, you're probably going to learn something new. So one of the things that I did was I went over, and I did this for Python 2.7, so I mean I really could do it again for 3, is I went over the libraries in the standard I went over a lot of stuff in the standard library. It was for my own benefit because I wanted to learn what was there, and I wanted to help people understand all of the different little niceties that are in the standard library to kind of help people to not have to reinvent the wheel more often than they needed to. And so that was a series that I did that took like months to get through. And it's probably worth repeating now that I have complete control over the videos now, and I can post them to YouTube. And there's more stuff in the Python 3 standard library that's definitely worth covering. So, all right. Thank you for coming, everybody, and we'll catch you in a couple weeks.